Hello everybody, welcome back to the channel. So in this video we're going to go over another calc basic, which is the math behind the derivative. In the last video we briefly explained what a derivative was. It's the slope of a curve at a given point. And so in this video we're going to get the math behind, show the math behind how we get a formula for this. So in any normal curve, let's say we just have a normal linear function like so. And let's say that this point is 1, 2. Say that this point right here is 5, 7, right? So the slope of this would be y2 minus y1 over x2 minus x1. Just your very basic rise over run here. And so we'd get, y2 minus y1, 7, minus 2 over 5 minus 1. So that's 5 over 4. For the slope of that. Okay. So that means that for every rise, 5 and 4. And that represents the slope of this here line. 5 up, 4 across. Okay, so let's try the same thing on something that's not a straight line. Let's try the same thing on this curve that we see right here. So I haven't given you a function for this. We can do that later. But let's just try the same strategy. So technically we used a secant line to represent the slope of this point because we used a line that went through 2 points and used those points to get the slope. So let's do the same thing here. So here, let's just pick 2 arbitrary points. To make it easier, let's just say this is y equals x squared. So we can say one of these points is what? 1, 1, and the other one's 2, 4, for the sake of simplicity. So now we connect. Oh, that was really bad. My apologies. Let's connect the lines. That's still pretty bad, but one last try. Okay, you get the point. So the slope of that line would be y2 minus y1 over x2 minus x1, so 3 over 2 minus 1 is 1, so the slope of that line is 3. So the slope of the secant line is 3. But that's not the slope of the function at any point, because it's an approximation, perhaps, of the slope of the function between x equals 1 and x equals 2, but it doesn't give us the slope of the function at any specific point, so it's really not approximate. So that's an interesting try. Let's go a little bit further. We're going to draw another y equals x squared curve. This time I'm going to pick 2 arbitrary points. I'm going to call it x and x plus h. So this x coordinate is x, and then this distance, this x distance, is h. So the coordinates for the first point would be x and then f of x. This function is y equals f of x. Sorry, this is a little bit confusing here. Let me try. Y equals f of x. And then this one right here would be x plus h, comma f of x plus h. Okay? There we go. Let's zoom out a little bit. There we go. Oops. Okay. So we have y equals f of x. Let me clean that up just a tad. Y equals f of x. This is x comma f of x. This is x plus h comma f of x plus h because we moved over a horizontal distance of h. So hopefully that makes sense so far. So the slope of the secant line connecting these 2 points, the exact same thing when we had numbers, would be, let's just use f of x plus h as the second y coordinate. So f of x plus h, y2 minus y1 minus f of x divided by x2 minus x1, x plus h minus x. So this simplifies to f of x plus h minus f of x all over, the x's cancel, so we just are left with an h. Okay, down a little more. So let's keep this expression in mind. So right now, this expression represents the arbitrary slope of the secant line connecting 2 points on a curve. Okay. So now we need to level up our approximation. So as I said, that it gives us a kind of decent rough estimate of, or an approximation of the slope between the points 1 and 2, depending on what you're using, but it's not at a point. It's not approximate like we got when we used just a straight line. So let's level it up. What we're going to try to do is turn our secant line, what we want to do, secant line crosses the function at 2 points into a tangent line. So how are we going to do this? We're going to do this with limits. So hopefully you learned limits in your pre-calculus class, and I will release a video about limits. But what we're essentially going to do is rewrite our, let's just rewrite our expression for that slope all over h, perfect. And now we're going to stick as the limit as h approaches 0. So as those 2 points on our curve get closer and closer together, so much so that the distance in between them is infinitesimal. That's a hard word. Extremely small. That distance between them is extremely small, so h is approaching 0. Then this will give us the slope of the tangent line at that point. At that point, x. Okay? And this is what we recall was the derivative. So, this expression right here that we just, to be cute, derived, it was an expression for our derivative. And that's how to get there. And hopefully this made sense, and we'll keep going in the next video. Thank you.